So for the next 2 hours or so, we're going to talk about stressing tendons and the elongation records. And the reason I did this webinar is in April of this year, I attended the annual PTI conference or convention, whatever it's called. And, you talk to people who do PT all over the country, and it's always fascinating because I'm sure like any other design material, you think you know what you're doing, and you show up, you say what you're doing, and you get laughed at and eyes rolling, and why would you do that? That's crazy. That's stupid kind of thing. But aside from that, the other comment or commentary there was in talking to PT suppliers, was a general, in my opinion, lack of understanding from basically the engineering community on what elongation records are, what they're meant to represent, how tendons are stressed, and how we actually get to the point. That force that we all, count on, design for, and obviously is there because our, post-tension slabs and beams work great. So my point in this webinar is to hopefully educate, obviously, but to help you not make, not that anyone here is doing that particularly, but not make more work for yourself, not increase liability, and not increase more work or liability for other people on certain aspects. And then also understanding what a measured elongation means, and especially what it does not mean. Because again, there's this kind of fluid dynamic understanding that I think is misplaced. And to people's defense, it's poorly explained in the code. It's, very mysterious, like most things in post-tensioning, because of, back in the day, it was a proprietary product. And so everyone kept the, secret sauce in-house. And, that kind of stuff just nowadays when PT is designed like anything else just causes a misunderstanding, confrontations that don't need to occur, and potentially work that doesn't need to occur. So the one thing about elongation records and stressing that I always found interesting is that, this is a snapshot of a typical two-way slab that I designed. It's currently in construction. Nothing, fabulous or amazing here. You have tendons in a two-way slab. Let me get my pointer. So you have 15 strands here, and based upon an effective final force, which means after stressing and all losses, you have 26.6 kips per strand. So if you obviously multiply by 15, you get 399. The same here, 7 will give you 186. And over here, 5 strands will get you 133. Those are the forces, again, after stressing, after wedge seating, after all the losses, if they take 20 minutes or, 20 months, whatever it is. When those occur, that's the force that we design for to A, satisfy the stress checks, but then B, as a basis for ultimate strength design. Those are the forces, the individual forces as a minimum that we care about. So in a lot of ways, the force that you put on your drawings is effectively the 60 KSI of rebar. Now, if you've ever looked at a mill cert for rebar, it's always 64, 65, 60, 6 or whatever it is. It's never 60. It's never exactly that because there's always a little fat here and there in the system. This is our 60 KSI. We're totally fine with 399 kips, but if you have a 407 kips of force, everything is still copacetic. Everything's fine. No big deal. So a lot of times I think this needs to be viewed more as the base minimum than the target gospel has to be this way. So obviously, because our force is dependent on the stressing, the elongations and stuff like that, we can't just say 60 KSI or whatever that equivalent is. We're putting a force into the system, and their job is just to make sure they're more than that force, not, hit it exactly or anything like that. So that's what we do as, structural engineers. Now, if you look at the structural drawings, as I said, we show the final effective force after everything. And that is primarily to design for stresses. It plays a part in ultimate strength, but much of a smaller part for reasons I won't get into. But basically, it's balance loads, pre-compression, P over A, stuff like that, and do the service stress checks. The force that we do not show, and to be honest, really don't care about from a numerical standpoint, is what the tendon force is immediately after stressing. What do they jack it to? After the seating loss, what's that force? because I can tell you with all honesty, it's substantially more than 26.6 kips a strand. It's going to start at 33,000 pounds or 33 kips and then migrate its way down to roughly 27 kips per strand. We don't specify any of that stuff as a number. We just say, based upon ACI requirements and stressing, don't go past X, Y, and Z, and these losses we're going to assume, you're going to get to that point that we show, but how you get there is kind of, up to you. Now, the jacking force is part of ACI. There's a table that I'll reference in a little bit in chapter 20 that basically says, it doesn't tell you what to stress to. It's kind of ambiguous. It basically just says, thou shalt not stress a tendon more than 80% of its ultimate, which is 0.8 times 270. So it doesn't really say you have to stress to that. You could be, technically 0.7 and 70% of FPU and satisfy the code. You just can't go past 80% of FPU, or apparently life as we know it is going to end, and the world's going to explode, stuff like that.